Okay, today we are simplifying radicals. So here is a nice little easy radical problem. The square root of 4 times the square root of 9. All right, so you think that's pretty easy. The square root of 4 is 2. The square root of 9 is 3. And 2 times 3 is 6. That's great. There's another way you could do this. You could decide that you could multiply the 4 and the 9 together and keep them under the square root. And get 36. And remember, the square root sign is still there because all you did was you did 4 times 9, got you 36. And now you're going to do the square root. And the square root of 36 is 6. So either way is possible. I generally like this way because I like to make things smaller. This second way, you're making the number bigger and then having to work with a bigger number. All right, so here's an example. We'll work both ways. Method 1. It's called the perfect square. So what you do is you look at 72 and you think of a perfect square that goes into 72. Now most of you will come up with 9 and 8. 9's a perfect square. You get 3, the square root of 9, and then you can't take the square root of 8. But be careful. The square root of 8 is not reduced. I can still take the square root of 8 and break it down into the square root of 4 times the square root of 2, and then this 3 is still on the outside. The square root of 4 is 2. We cannot take the square root of 2, so my final answer is 6 radical 2. See, that way it's called perfect squares because I always try and find a perfect square. Primes is kind of like you were back in 6th grade. And we take the number 72 and we break it down like a factor tree. All right, keep going with this factor tree. And I'm broken down into primes. So what I do now is I circle pairs of numbers. And since square root means 2, that's why I'm circling pairs. So square root means 2. So, wow, look what 3 times 3 is. It's 9. And look what 2 times 2 is. It's 4. Aren't those the perfect squares that I ended up working with over here? So with the primes way, 3 times 3 gave me 9, so I must have a 3. 2 times 2 gave me 4, so the square root of 4 is 2. And then look at this little 2 right here. Nobody to pair up with, so it has to stay in the radical. And we came up with the same answer, 6 radical 2. Now when you do the perfect squares, you always want to try and find the biggest perfect square. So if you're not sure about your square roots, there's a handy dandy little chart here. And I will end the video on this chart, so if you want to copy it down. So here's my squared chart. The second column represents all my perfect squares. So what you would do is, let's say you had the number 72. You would go through this list and find out, does 4 go into 72? Sure, but 9 goes into 72. Okay, 16 doesn't, 25 doesn't. 36 goes in. 36 times 2. And if I had used 36 times 2, square root of 36 times the square root of 2, I could have gotten to 6 radical 2 right away. But the point is, it works no matter what you use. It may just take you a little longer. All right, let's try another example. Perfect squares. I've got this 5 out front, and now I've got to think of perfect squares that go into 48. Well, if I come back to my table, okay, 48, well, 4 goes into 48, 9 doesn't, 16 does, 25 doesn't, 36 doesn't, and obviously I'm too big here, 49, so my biggest perfect square that goes into 48 is 16. Wow, there we go. So it would be 16 times 3. 5. Can I take the square root of 16? Yep, I get 4. Can I take the square root of 3? No, so it stays there, and I get 20 radical 3. All right, so perfect primes would be our lovely factor tree. So I'm going to take the 48, break it down into 16 times 3. 16 is 4 and 4. 4 and 4 would be 2 and 2, 2 and 2, and 3. So now I'll pair off my numbers because perfect squares mean to pair. There's one pair, there's another pair, and radical 3 does not get a pair. So that means 4, square root was 2, 4, square root was 2, radical 3, I get 4 radical 3, but here I got 20, oh that's right, I got to bring this 5 down from up top, and that gets me 20 radical 3. So I'm not a big fan of the primes method. I really like this perfect squares method because it's, look how much shorter it is. All right, perfect square. Wait a second, where did all the numbers go? Well, x squared, square root means 2. So x to the 4th. I got to think of 2 things that multiply together to get me x to the 4th. And one of them has to be a perfect square. Oh, x squared and x squared. What is the square root of x squared? X. What is the square root of x squared? X. So the square root of x to the 4th is x squared. Okay, if you're going to do primes here, x to the 4th would be broken down into x, 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 x. I'm going to circle pairs of numbers. That is a perfect square. That is a perfect square. So I'm left with x times x is x squared. All right, so we got a little side note here. So take your time, pause the video right here, and write this down. Since taking the square root of a number is the opposite of squaring a number, then the square root of an even power will be half the exponent. Divide by 2. Did you see that? All we did was take x to the 4th. We take the exponent of 4, we divide it by 2. So the square root of x to the 4th is x squared. Okay. All right, here's another one. Perfect squares. Well, now we combine things. We have a number and we have a variable. So we're going to work each one individually. So 20 is the square root of 4 and the square root of 5. Perfect square is 4. You always, always, always have to pick a perfect square. So that's 2 radical 5. And now, what's a perfect square that goes into x to the 5th? Well, x to the 4th. That goes back to that little slide I just told you to write right here. An even power will always be a perfect square. So x to the 4th and x. The square root of x to the 4th is x squared, and then poor little x right here doesn't have anybody to take a square root of. So now if I put it all together, I have a 2 and an x squared that goes on the outside. And what's left over in parentheses? A 5 and an x. All right, I'm going to skip the primes for now because I really want you guys to work on the perfect squares. So let's get rid of these primes here. And let's just do the perfect squares. Okay, so break it down. I have to look at the 4. I have to look at the x squared. And oh my gosh, now I got a third in there, a variable of y to the 7th. All right, so let's look at one thing at a time. All right, let's look at this first. X to the 4th is 2. Okay, let's take the square root of x squared. That's x, because it's an even exponent, and we just divide by 2. All right, now the last one, y to the 7th. All right, so I'm going to have to break y to the 7th down. So I'm going to pull out an even exponent of y to the 6th, and then y. The square root of y to the 6th is y to the 3rd, and then this y has nobody, can't take the square root of a single y. I have a 2 and an x. And that's my answer. Oh, look at this one. Anybody notice what's different about this one? Yep, it's a cube root. So now I have to go back to my chart right here and realize that I'm not using perfect squares anymore. I've got to use the perfect cubes. Okay, so let's go back to that slide and let's see. The 1/2 is hanging out here, so we'll let it hang out there. I got to take the cube root, and then I'll put the 24 in there. I'll take the cube root, and then I'll put x cubed. I'll take the cube root, and I'll put y to the 8th. All right. The cube root of 24. Find the biggest cube that you can think of that goes into 24. All right, so I'm going to come back here. Look on my cubed. 8 goes into 24. 27. 27 can't go into 24, so my biggest perfect cube is 8. So 24 cube root would be broken down into the cube root of 8 times the cube root of 3. All right, can I take the cube root of x cubed? Absolutely. I get an x. Because all I'm doing is taking the 3 and dividing it into the 3. So what I did was I took this 3 and divided it into that 3. And it goes in there once. So I get x to the first power. Now, what about this one? I got to find a perfect cube. Well, if I did the cube root of y cubed, because we know y cubed is a perfect cube, then that would leave me with the cube root of y to the 5th. Right? Because you add exponents, 3 plus 5 gets you 8. But guess what? There's a y cubed inside of this. So I could have really made it another cube root of y cubed and then a cube root of y squared. Because look, 3 plus 3 is 6 plus 2 more is 8. Can I take the cube root of y cubed? Yes. Can I take the cube root of y cubed? Yes. Can I take the cube root of y squared? No. There's only 2 y's there. That's not enough to take a cube root. I need at least 3. So this stays in the cube root. Here's my 1/2. The cube root of 8 is 2. And can I take the cube root of 3? No, I can't. It's not on my perfect cube list. All right, so let's clean this up. 1/2 of 2 is 1. I have the cube root of 3. Y, whoops, let's don't forget this x. I have an x, a y, and a y. So on the outside I have x and y squared. And then I have a cube root of y squared, so I don't have to write a cube root symbol over again. I'll just add a y squared to that cube root. All right, so that's the end of the video. I'll leave the video ending on this if you would like to take a screenshot of this and print it out. It's a list of your perfect squares, your perfect cubes, and your perfect fourths.